Okay, guys, hey, today is chapter 1. I'll just tell you that we're going to do 2 sections from chapter 1 and 2 sections from chapter 5. Again, 4 sections, and then we'll take a test over. So it's not a real long chapter, okay? Kind of like the last section was, or the last test. It wasn't very long, not that many sections, but a lot of important material, okay? Today, our objectives are to identify families of functions. Okay. The other one is to describe transformations of parent functions and describe combinations of transformations. Okay. So the first idea that we're going to talk about is this parent function thing. A parent function is the most simple. Actually, I like basic. Sorry. The most basic function in a family. Okay, so we're going to talk about different types of functions that are in math and get a general idea of what they look like. Okay, and then we'll talk about some transformations of those parent functions. Okay, domain is a word that we've heard before, and the domain is the set. And in math, the word set really just means list. Okay, so if you want to maybe put in parentheses here, list, it's the list of all x values of a function. So domain is talking about the x values. Okay. The next word is range, and the range is the set, or again list, of all the y values. Now, how do I keep those separate? Well, x and y are pretty simple. Okay, we use those all the time. And I know that x comes before y in the alphabet. Would you guys agree there? Now, domain in range, what comes before it in the alphabet, or what comes first, D or R? D. So domain is referring to the x, and the range is referring to the y, again using that alphabet trick. And another phrase that we kind of use between those two are inputs and outputs. Okay, what comes first in the alphabet, I or O? I does. Inputs and outputs. So these three terms, x values, domain, and inputs, are all synonymous with each other. They mean the same thing. Okay, y range and outputs mean the same thing. Okay, now a transformation of a function changes, if I can find my notes, which I don't have, it changes the size, shape, position, or orientation of a graph. So in geometry, most of you have already taken geometry, we talked about different types of transformations. Okay, a translation, where we're sliding it up and down. What other transformations did we cover in geometry? Which one was it? I said translation, where we just slide it. Dilation, where we make it bigger or smaller. Yep. Reflection, where we flip it over a line. Rotation, which we won't really cover it right now, but that is also a different type of transformation. Now, guys, we've got two key charts. The first one's here on the front page. Okay, now all these are our different types of families of function. Okay, the first one is a linear function. Okay, now a linear function is just like f of x equals. Now, when I say f of x equals, raise your hand if you've seen that before. Okay, most of us, which is better than the other class. What is f of x? Does anyone know? Anyone put in their own words? No? When I was in your guys' shoes, I was so confused by this. Because our whole lives, up until this point, we say, hey, y equals. And now all of a sudden, they just like switch gears on us and start saying f of x. But f of x just represents y. It doesn't mean f times x. Kind of looks like that. It doesn't mean that. Basically, what it means is it says, hey, it's a function, that's the f part, with respect to x. X being our input value. Okay? We could do f of n if we wanted. Again, n represents our input value. F of b, f of whatever. Okay? And it just represents a y. So don't be confused by that. It's just another way of saying a y. So a linear function is just x. There's not x squared. There's not the square root of x. It's just x. And if you think back to last chapter, when we were graphing linear equations, everything was like 3x plus 4. Okay? Or 4x plus 5y equals 16. There's just x's and y's. Okay? Now, when we graph a linear function, the graph y, again, this represents y. The graph y equals x. What does that look like? Straight, what'd you say? A diagonal line, absolutely. Good, Ralphie. I thought you said dotted for a second. A diagonal line. It goes through the origin, 0, 0, and it's got a slope of what? Slope of 1. Who said that? Easton Oz. It's got a slope of 1. Now, we can transform that. We can slide it up or slide it down or change the slope so it's steeper or not as steep. Okay, we can transform that, but that's the parent function. Every linear function comes from this. Just like we come from our parents, every linear function is going to come from this. That's the parent function. Okay, now, I'm going to come back to transformation. I'm going to skip that. I'm going to try something different. Now, domain. Okay, we just said that the domain is a list of all of the x values. Okay, so if I take a look at the graph, if I look at 1 there, is 1 at 1, an x value, is the graph at 1? Meaning, does the graph go to 1 on the x-axis? I think it does. It's right up here, right? What about 2? Is the graph at 2? Yes. What about 3? Yes. 4? Yes. 5? Yes. 19? Yes. 327? Yes, the graph's going to keep going, right? So I'm looking at, hey, what x values going side to side is the graph? Where is the graph there? Okay, so I think the graph is all x values to the right because this is going to keep going forever and ever and ever and ever. What about over to the left? Same thing, right? That line, you guys agree with me, that line is never going to stop. Okay, so our domain is all x values. So one way to put that is in what we call interval notation. I'm going to say, hey, the smallest is negative infinity. Would you guys agree that the smallest number, and it's not really a number, but it's just a place, is negative infinity? Yes or no? And the largest one is positive infinity. So basically what I'm saying is, hey, our domain, every x value can be used here. Now, another way to write that, I think it's a better way, is just this idea where it's, hey, it's all real numbers. And I'll probably use that more than saying negative infinity to infinity, but we might see or might come across both of those. Now, our range. Our range is our y values. You know, y values is the graph using. Well, if I look at my positive y values, again, is this graph ever going to stop? It's going to keep going, up, 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 until it can't go no more. So my largest range is what? Positive infinity. If I look at my negative y values, or my negative range, is it ever going to stop going down? No. So again, my range is all real numbers. Questions there? Again, I got a lot coming at you today. Okay, so if you got questions, stop me. The second parent function is this absolute value function. So our parent function is f of x equals the absolute value of x. And again, those vertical lines represent absolute value. Okay, now an absolute value, anyone know what an absolute value graph looks like? I'm sure we did these in Algebra 1. You get 10 imaginary extra credit points, whoever can answer that. Shape is in a V. I don't know if I can give you the credit for it since I had already started drawing, but I'll give you 2 imaginary extra credit points, Jesse. It's a V. Now, let's look at our domain. What x values are being used? Side to side. So this, what's my smallest x value? Negative infinity. That thing's going to keep going. What's my largest x value? Infinity. So my range, my domain is all real numbers. If there's an arrow going that way, it's going to keep going forever. If there's an arrow that way, it's going to keep going forever. Domain is all reals. Now what about my, domain is all reals. That's what I said. What about my range? Does the graph go down there? No. So therefore, my range, I'll say this, what's my smallest range? My smallest y value is 0. Now, this is going to be a little new. We're going to use interval notation. Now, is 0 being used? Does the graph reach or get to 0 on the y? It does. It does get to exactly 0 and then it hits it. So we're going to use a bracket. The bracket represents, and the bracket says, hey, the range in this case gets to 0. It actually, physically, 0 is in our range. Now, just watch this. If it was like this with a parenthesis, it means, hey, 1 is in our range, 0.5 is in our range, 0.25 is in our range, 0.1 is in our range, 0.05 is in our range, 0.000001 is in our range, but then as soon as we get to 0, it's no longer in our range. But since it's a bracket, it says, hey, 0 is included. So everything up until 0. If it's a parenthesis, we can get really close to 0, but we're not including 0. Okay? So since it's including 0, we're going to use a bracket. Now, what's my highest range? Infinity. Now, can we ever get to infinity? No, infinity is a far place that we'll never get to. So we can't actually get there, so we're going to use a parenthesis. Questions, comments, concerns there? A quadratic. What the world does that mean? No, good guess. I can see why I say it. Quad. I get that. Quadratic means it's a function that is x squared. Okay, so we have a function that's x squared. Well, that's what we call a quadratic function. Now, Jesse said it's in the shape of a U. The math term is a parabola. Repeat after me. Parabola. Oh, everyone wasn't participating. Parabola. And it looks like a U. Now, I could get into why it's the shape of a U. If you have questions about that, I'd love to dive in there. That's not really why I'm doing this section. I just want you to understand basic shapes of basic parent functions. Okay, now, let's look at our domain here. Domain. What x values are being used? What about my negative x values? Is that ever going to stop? It's going to keep going up, and it's going to go over slightly. Same thing here. Positive x values, it's going to keep going. So my domain is all real numbers. My range, again, are negative values in my range? No. So same idea, 0, with a bracket, that's my smallest range, and then my highest range is infinity. Because it's going to keep going on forever and ever and ever. Okay? Okay? The next is a cubic function. A cubic function is something that is cubed, x cubed. Okay, a cubic function looks like this. Mr. Went, does that have a name? I have to put you on. I can't think of either. That's a parabola. There's other name. I can't think. I'm having a brain fart of what that's called. Okay, now look at our domain and our range. Our domain going side to side. Well, there's arrows on both sides, right? So that means it's going to continue to stretch forever and ever. So that's going to be all real numbers. And then my range, again, there's arrows on both sides. So that's going to be all real numbers. The last one is a square root function. So f of x equals the square root of x. Square root function looks like this. Our domain. What's my domain here? Side to side, I'm talking x values. What's my smallest domain? 0, right? So my smallest domain is 0. Again, I'm including 0. What's my largest? My largest x value is infinity. Now range, going up and down, smallest range is, again, 0, including 0. My largest is infinity. Main idea with this front chart. A, parent functions. What are the different kinds? What are their names? And B, what do they look like? Okay, we talked about domain and range just to get an introduction to that as well. Main idea is the general shape of parent functions. Okay? Now, this next chart, okay, is talking about transforming different functions. Moving, shifting, flipping, making things wider, all the different transformations that can occur. Okay, so the first one that I'm talking about is a vertical shift. Vertical goes which way? Up or down, okay? So in words, what is a vertical shift? Well, I'm going to say shifting, and I'll say actually a slide, sliding up or down. Now, how do I write that in function notation? It's whatever function we have. Okay, I'm just writing this in general form. It's our function. It could be x squared, it could be whatever, but then it's going to be plus a number at the end. We call that k. So if there's a number after the function that sits all the way in the back, all by itself, that's going to move the function up or down. Okay, here's where our colored pencil comes in handy. Transformation form. On the right there, I've got a function that says f of x equals x plus 3. What's our parent function? It's a linear function. Would you agree? It's just x. I want to use your colored pencil to draw the parent function. The parent function goes through the origin and has a slope of 1. That's the parent function. Okay, now this k value, this plus 3, is going to shift it 3 values which way? It's going to go up. 1, 2, 3. There we are. Now, would you guys agree that we already knew that? We already knew this is in slope-intercept form, right? F of x or y equals mx plus b. So we go up to 3 units on the y-axis. Our slope is 1. It's shifted up 3. Questions here at all? Again, there's a number at the very, very end. We're going up and down with it. Next idea is this horizontal shift. So a horizontal shift means we're sliding left or right. Okay, now, if we're going to go up or down, it's at the very, very end. If we're going to go side to side, it's going to be inside the parentheses or square root sign. Okay, so it's going to be like this. F of x plus, actually no, excuse me, minus h. So if there's a number that's adding or subtracting from x inside the parentheses, we're going to go side to side. Now the big idea here is if it's inside the parentheses, we need to star this, it is a liar. It's actually going to go the opposite direction that you may think it will go. Okay? So, we've got f of x equals the absolute value of x plus 2. Now, notice how this plus 2 isn't at the very, very end. Okay? If it was plus 2 out here, we would go up and down with it. But since it's in the absolute value signs, in the parentheses, absolute value signs essentially act as parentheses, we're going side to side. Okay? So let's first draw our parent function. Parent function here, Ralphie, is what? Our parent function is, look at our front page. You've already, the linear, quadratic, absolute value, square root. Absolute value in the general shape of an absolute value, Owen, is what? It's a v. So my parent function is going to be a v. Now, this plus 2 is going to shift it 2 units which direction? Where? Now, if it's at the very, very end, it's going to go up or down, Melissa. But since it's inside the parenthesis, and we're talking about horizontal shift, we're going to go right or left? Left, because it's a liar. So we're going to go left 2, 1, 2. Do we see how this is inside the function itself? Yes or no? Plus 2 is inside. If it would have been outside, it would look like this. Absolute value of x plus 2. That's what it would look like if it's outside. That's going up 2. Okay? Next one. Reflecting it over the y-axis. Okay, reflecting over the y-axis. That, in other words, means flipping over the y-axis. Okay? That means we are going to have a negative sign inside the function before the x. If it's inside, we reflect over the y-axis. So here we go. Again, what's my parent function here? Can I change this? I don't want to do that. I want to change that. Let's do the square root of x, and actually the square root of negative x. That's my parent function. So what does that parent function look like there, Sadie? Yeah. I think the best way to describe that is do one of these. Kind of does one of those with their arms, doesn't it? Parent function looks like this. Now, since there's a negative sign in front of, but it's in front of x, but it's inside the function, we're going to reflect it over the y-axis. So it's going to look like that. Reflecting over the x-axis, that's going to be flipping over x-axis. Now, how does that happen? Well, that means that's going to have a negative in front of the whole entire function, way out in front. So if there's a negative way out in front of the thing, then we're going to reflect over the x. If it's inside the function in front of x, then we're going to reflect over the y. So my general or my parent function here is absolute value. Again, we've already talked about that. That's going to be a v. Now, if I reflect it over the x-axis, it's going to look like this. So instead of opening up, it's actually going to open down. Two more. Vertical stretching. If I'm stretching something vertical, it's going to get skinnier. Would you guys agree there? Yes? No? I had some putty or like some pizza dough, and I were to stretch it, isn't it going to get skinnier? Okay? So a vertically stretch makes it skinnier. And here's how that happens. If we have a function, let's just call it a general function f of x, and there's a number in front of the function. Okay? We're calling this an a value. Now, it'll make it skinnier if the a value is greater than 1. Now, let's pretend this 3 wasn't here. What number is in front of x squared now? 1. There's a 1 there, right? We don't show it most of the time. There's a 1 there. Okay, so 1 is kind of like our normal standard width. It doesn't change anything. But now, as soon as we have a number there that's greater than 1, it's going to make it skinnier. So here we go. If I have 3x squared, let's draw our parent function. Parent function is quadratic. What's the shape of this graph called again? A parabola. And then that 3 there, since it's greater than 1, is going to make it skinny. Horizontal stretch, that's going to make it wider. So if I horizontally stretch something, that'll make it wider. Again, that's when there's a number in front of our function. And again, we consider that number like an a value. Now, the a value needs to be between 0 and 1 for it to be wider. So basically, it's a fraction between 0 and 1. It's not 0. Excuse me. It's not 1. It's somewhere between. So if I look over here, last one. I've got x squared. That's my parent function. So it's a quadratic shape of a parabola. And now since there's a 1/2 there, it's going to make it wider. Now, how much wider? I'm not concerned about that. I just want you to understand, oh, there's a 1/2 there. It's going to be wider. Guys, we're going to go back to the first page here for a second. I want to fill in this last column, second to last column, I should say, the one that we have filled out. It's called transformation form. Okay, basically what I'm going to write down is I'm going to write a function down with a bunch of letters. So it looks like this: a times x minus h plus k. Wow, there's a lot of letters there, isn't it? But we just covered each one of those letters. What's the k do? Well, check our chart on the other page. The k does what? Moves it up or down. What's the h do?
Slide it.
Left or right, and the important thing about the h value is what? It's a dirty liar. It's going to be opposite of what it's telling us. And then our a value will do a couple things. It'll make it skinnier or wider depending on what the value is. And then if it's negative, if the a value is negative, what will it do? If the negative is way out front, it's going to reflect it over the x-axis. If there's a negative inside, it's going to reflect over the y-axis. So absolute value is a times the absolute value of x minus h plus k. Again, we've already talked about our k, we've already talked about our h, we've already talked about our a. Quadratic f of x equals a times x minus h squared plus k. Cubic f of x equals a times x minus h cubed plus k. And lastly, our square root, a times x minus h, oops, let me rewrite that. Square root of x minus h plus k. Guys, when we start doing our assignment, these two charts are going to be important. The first one, general shapes of functions, of parent functions. I think that's pretty easy. We need to use this second chart like it is a rule book. Okay? This will tell us everything that we need to do. Let's go and get into some examples. Guys, I got, starting now, I took all this from the book, and then I added these charts in later, and really, now that I think about it, I really probably didn't need all this because I just talked about it all in the chart. Okay, we'll just kind of zip through this. I might skip some. But first of all, example 1 says, identify the function family to which each function belongs, and then compare the graph to the graph of its parent function. So if I look at the left there, what is the parent function? Absolute value. It tells us in the equation, right? So I can look at the equation, and it says absolute value. See that, Luke? Says absolute value there in that function, 2 times the absolute value of x plus 1. Or we could have recognized its absolute value by what? Shape of the graph, right? So I'm right, absolute value. That's the parent function. And then, how does this function differ than the parent function? Say it again, Owen. Boom, it's up 1. How'd you know it's up 1? You look at the graph, or we could have looked at what? The plus 1 at the end. This plus 1 right there tells us it's up 1. How else does it differ? Jules, how else does this function differ than the parent function? Okay, I would agree. There's a 2 in front of the x. How does that change our function? How does it change our graph, though, Jules? No idea? Alyssa, do you know? How does the 2 alter or change our graph? No idea? Sydney. Makes it skinnier. Would you guys agree? Go back to our chart. Go back to our chart. If there's an A value in front that's greater than 1, it makes it skinnier. So I'm going to put skinnier. Is skinnier a word, or is it more skinny? Sometimes I say stupid stuff like that and I forget that I'm being recorded right now. So, absolute value function. Now, how does this differ than the parent? Well, it's up 1 because of the plus 1, and then there's a 2 in front, which makes it skinny. Okay, let's look at the next one. Josh, what's our parent function here?
1 plus x.
What's our parent function on the very, very first one, on the very first page? We've got, I think, 5 different ones. It's not linear. There's a squared. Which one has an x squared on there? Yeah, this is a quadratic. That's our parent function. Quadratic because it's got an x squared. Okay, now, how is this graph different than its parent function? Trayla? So what does that do, though? I agree. Moves it horizontally. Which direction? Yeah, it moves it right. So she noticed that we're subtracting from the x inside, so she knew that's going to be a horizontal shift. If it's a horizontal shift inside the function, inside the parentheses, it's a liar, so it's right 3. Right 3. Ralphie, what's this 1/4 going to do out front?
It's going to make it wider.
It's going to make it wider. Great. How do we know it's going to be wider?
It's less than 20.
Great.
Less than 0.
I'd say between 0 and 1. Between 0 and 1. Questions there? In a nutshell, that is what we're doing today. Now, what I do now is I break down each individual translation, or I should say transformation, into by itself. So the first thing is talking about a translation. We've really already talked about that. I know that if it's going to be after the function, it's going to shift it which directions? Peyton, can you tell us? If it's after, it's going to shift it. That's fine. Look at our chart. Up and down or side to side? Sadie, can you help her out? If it's after, it's at the end. Shift which way? Up or down or side to side? Agree or disagree? Everyone turn to your chart, your second chart. Your first chart's nice and handy. You won't use that much. I'll just be honest with you. If I look at my first chart, see where it says function notation, it says plus k. And then I go over to my example and it says x plus 3. Those happen at the end. Would you guys agree with me there? So that means we're shifting up or down. So this graph is at the very, very end. X is my function, my parent function, minus 4. So we need to, if I'm going to graph my parent function, it looks like this. No. Talk about slide. Yeah, no. Now from here, I know it's shifted which way? Down 4. So 1, 2, 3, 4. There we go. Now there's my actual. Now here, I know my parent function is a what, Easton? Parent function is quadratic, which is going to be a u. So if I just draw my parent function in there, it looks like this. Now, the minus 2 shifts us which direction? Jaden? To the what? Do you agree or disagree with Jaden? Why is it to the right, Jaden? Why is it to the right? Because it is a liar. Remember, we said that if it's inside the parenthesis on our chart, it's a liar. We're going opposite. So now I need to shift it 2 units to the right. Questions there? If I wanted, it's a shift or slide. If you want to fill that in, a shift or slide is what a translation is. A reflection is a flip of a graph over a line called the axis of symmetry or axis of reflection. Basically, it's the line that we're flipping it over. Okay, here, if the negative sign is way out in front, we're going to flip it where? Over the x-axis. So my parent function is a parabola, looks like so. And we're going to reflect it over the x, because it's way out in front. Looks like that. Now this is the same thing. Let's change this. Let's do absolute value of negative x. So now where's the negative sign? It's inside, isn't it, Josh? Yeah, the negative sign's inside. So my parent function is a v, right? Absolute value. Now if it's inside, I reflect it over what? The what? The y-axis. Now, if I reflect this thing over the y-axis, that means this part is going to be over here, and this part's over here. Has it changed at all? No, it's actually going to be right on top of each other. So it's kind of unique. It doesn't really change it because it's just going to flip it. Okay, a vertical stretch makes a graph skinnier. Or taller. A vertical stretch makes the graph wider, or if you want to consider it, shorter. So again, if our a value, the value that's in front of the graph, is greater than 1, what happens? It gets skinnier. So I'm going to graph this. Here's my parent function. Now, guys, I will say this, okay? If we have an absolute value function, aren't those made of straight lines? Isn't an absolute value made of straight lines? Kind of 2 rays, if you will. This number represents the slope of the graph on the right-hand side. Okay, so I know I'm going to make it skinnier, and I know the slope is going to be 2. So I can go up 2 over 1. up 2 over 1, up 2 over 1. Now the other half is just going to be negative 2. So if I go up 2 that way over 1, up 2 over 1, up 2 over 1. Again, that only works if it's an absolute value. Now, notice that it's not f of x, it's m of x. That's the same thing. No different than f of x, m of x. Here I have p of x. Now, my general function, my parent function, is a parabola. Now, since my a value, the value out front, is between 0 and 1, it is going to make it wider. Now, how much wider? I'm not concerned about that. Just so you know, it's going to be wider. Last one. Okay, it says use a graphing calculator. I'm not going to do that. I want us to do this by hand. First of all, our parent function's what here? Absolute value. That's in the shape of a V. And if I'm being accurate, the parent function has a slope of 1. So it should be like that. Okay, now we've got multiple transformations that's occurring. Okay, I'll say this, guys. If we have a reflection, we want to do that first. We want to do that reflection first. Do we have a reflection? Sydney? Yeah, over x-axis or over the y-axis? Over the x. It's way out in front. That means there's going to be a reflection over the x-axis. So it's going to open down. Okay? Now, Jules, can you tell me another thing that we're going to do to this graph? I've already said it's going to reflect over the x. What's the number at the very, very end do? No? No. That's only if it's inside the function. The number at the very, very end of the function does what? Up or down. Up or down. The very, very end, up or down. The very, very end, up or down. Very, very end, what do we do? Up or down. So here it's going to go down 3. But hold on here. We've got multiple things that are occurring. We just don't want to go down 3. What's the 5 do? It's inside the function, so that's going to go left or right. But we know that if it's inside, it is a liar, so it's going to go to the left. So, here we go. This takes it left 4. 5. 5 units. 1, 2, 3, 4, 5. This takes it down 3. And I know it's going to open which direction? It's going to open down. Questions on how we did that? Okay, if I look over here. Guys, what's the negative 2 going to do at the very, very end? Up or down. So it's going to go up or down. Which one? Down 2. Okay, so first of all, let's do our parent function. It's a quadratic. The 2 here is going to shift it down 2. Alyssa, what's this negative 4 going to do? Alyssa? Move it to the right. Again, it's a liar. It's inside. So it's going to go right. So we're going to go right 4, down 2. What's this 3 going to do, Sadie? Now flip it. Sydney? It's going to make it skinnier. How do you know it's going to make it skinnier, Trayla? It's greater than 1. If there's a number in front, it's going to make it wider or skinnier. Either one. If it's greater than 1, it's going to make it skinnier. So here we go. It's going to go right 1, 2, 3, 4. Down 2, 1, 2. Now it's going to be skinnier.